All right, so we are moving on to phases and pressure, specific volume, and temperature relationships. Three phases of matter: solid, liquid, gas. We'll talk about phase changes in this class. If we're going from a solid to liquid, it's melting; liquid to gas, it's evaporation or boiling. If we're going the other way, gas to a liquid, it's condensation; liquid to a solid, it's freezing. Now in this class, we're going to primarily focus on the phase transition between liquid and gas. And it's important to note that for that phase transition, both of those phases are going to be present at the same time in equilibrium during that phase change process. So you'll have part liquid, part gas while it's either evaporating or condensing. This is a picture in your book, a three-dimensional representation of how pressure, specific volume, and temperature are related to one another for a given substance. So the substance that we're going to primarily focus on is going to be water. We'll look at other substances as well, but we'll talk a lot about water in this class. And so you could see this like shaded portion in the middle, this sort of dome-like structure. This is our vapor dome. We're going to look at that in a little bit more detail momentarily. But what I want you to take away from here is that all of these properties are related to one another: pressure, specific volume, and temperature. So let's kind of it's a little difficult to get anything out of this just because this three-dimensional graph, right? So let's look at just a projection of two of those properties. So let's just look at pressure and specific volume. So again, we're taking what's on this three-dimensional representation and we're just looking at the pressure and specific volume. So it's a projection of just those two properties. All right, so here's that vapor dome. Remember the vapor dome kind of in this dark orange over here. But this is our vapor dome. And let's look at more than two regions. So to the left of that vapor dome, we have liquid. We have fancy names in thermo for liquid. So you'll hear compressed liquid, subcooled liquid, or just plain old liquid. It's liquid. That's what it is. But we give it fancy names. But just at the end of the day, it's just liquid. If it is underneath that dome or on the dome, we call it saturated, and it just means that it's going through that phase change, and both of those phases, liquid and vapor or liquid and gas, are present at the same time. On the right, or to the right of that dome, we have a gas. We also call that a superheated vapor, but again, it's just a gas. Okay, so just make sure to note that even though we have these fancy names for liquid and gas, at the end of the day, it's just liquid and gas. All right. So if you look at that pressure, specific volume, PV diagram on the left-hand side, you can see that like blue line there. So if you're right on that line, then we call it a saturated liquid. So a saturated liquid doesn't look any different from a liquid, but we categorize it as a saturated liquid because it is about to boil, but it hasn't quite yet. It's on that tipping point. And conversely, if we're on the right-hand side of that dome, we call it a saturated vapor. It doesn't look any different from a gas. It's all gas or all vapor, but it is about to condense. If we move to the left, it would condense. All right. Underneath that dome, if it's not on the dome, if it's not on the dome and it's just underneath, then it's also saturated. So if it's on the dome or it's under the dome, we categorize it as saturated. But if it's just under the dome and not on that line, then it's saturated and it contains both saturated liquid and saturated vapor, some mixture of the two, right? The further you are closer to that saturated vapor line on the right, the more saturated vapor you have, and the closer you are to the saturated liquid line on the left, the more liquid you have, or saturated liquid you have. All right. So remember this PV diagram, it came from a three-dimensional representation. We had pressure, specific volume, and temperature data. So the temperature data didn't go away. So let's look at what that actually kind of looks like. We're looking at a two-dimensional representation, so just keep that in mind. It's not gonna, it's a projection of where that temperature, the temperature trends are. Okay, so if I were to draw a line of constant temperature on this PV diagram, it would look like this. So you see that the tails sort of, it flips up on the left-hand side and it flips down on the right-hand side, but it's straight across in that two-phase region. I could draw another line of constant temperature, right, at another temperature. T1 and T2 are different, but as far as which one's bigger, well, it's kind of what you would think. T2 is bigger than T1. All right, so a couple of things to note here. If we're in this two-phase region, if we're looking at a process, say we're looking at a process from let's look at T1, okay? So if we're looking at a process where we go from a saturated liquid, right on this line, to a saturated vapor, if it's a constant pressure process, right, so pressure's on this side, so if it's a constant pressure process, it's going to go straight across, and it's going to be on that line of constant temperature as well. So if the pressure is constant, so is the temperature. And another way to think of this is if we are in this two-phase region and we're at a given pressure, so say we're at this pressure right here, and I know I'm two-phase somewhere in this region, okay? I don't know where I am on that region, but somewhere on that region. At this particular temperature, there's only one possible temperature that I could be at, and that's at that T1 if it's going to be saturated. All right. And that's what I just said. So we call that temperature a special name. It's our saturation temperature at a given pressure. So we'll say Tsat at P1, okay? But this temperature right here is the saturation pressure. It is the pressure at which we will boil or condense. Well, not we personally, but our substance here. It is the temperature at which that substance will boil or condense if we're at this pressure P1. Okay. All right, let's look at a TV diagram. So again, we have that three-dimensional representation of temperature, pressure, and specific volume data. We're just going to pull out the TV data right here, okay? And this is our vapor dome, and it's the same, goes along the same kind of line of reasoning. On the left-hand side, that's our liquid region, or our compressed liquid or subcooled liquid region. If we're underneath that dome, that's our saturated substance region, I guess. It's our two-phase region. On the right, that's our superheated gas. Our saturated liquid line is on the left-hand side of that, or on that left-hand side of that dome. Again, a saturated liquid, it's all liquid, but it's about to boil, so we give it a special name. On the right-hand side of that dome, that's our saturated vapor. It's all gas, but we give it a special name because it is about to condense. All right. If we're underneath that dome, we have some mixture of saturated liquid and saturated vapor. All right, so now let's look. We looked at the lines of constant temperature on a TP diagram, or I'm sorry, a PV diagram. And now we're going to look at the lines of constant pressure on a TV diagram. Because recall, this information right here came from that three-dimensional representation of temperature, pressure, and specific volume. And we've pulled out the TV data, but now we're going to remember, oh yeah, there is pressure data. I still have that, okay? So this is the trend line for lines of constant pressure on a TV diagram. You'll notice that the tails are flipped, right? With the lines of constant temperature on a PV diagram, they were the opposite way. Let's go look at that actually. Yeah. So you see they went down, straight across, and then down again. On our TV diagram, let's go back over here. You see they go up, straight across, and then up. Okay. I can also draw another line of constant pressure here. And as far as which one's bigger, P1 or P2, P2 is bigger. Right, so it's the same as the lines of constant temperature on a PV diagram. the trend with which one's bigger is what you think it is, right? Okay. Let's see what else we want to say. All right, so takeaway messages here. If we're in that two-phase region and say we're going through a process, maybe from a saturated, we could be going from a saturated liquid to a saturated vapor, or maybe just from this point right here to this point right here, right? Some mixture of saturated liquid and saturated vapor to this mixture of saturated liquid and saturated vapor. If it's at a constant temperature, the pressure has to be constant too, because at a given temperature, at a given temperature, there's only one possible pressure that you could be at and be saturated. So if we're at this T1 and we know we're saturated somewhere in this region right here, I know there's only one possible pressure that I could be at, and it's that saturation pressure. So again, we give it a special name. We call it PSAT at that temperature at T1. Okay. All right. So where's all this going? This is all going to be able to, you could see that the pressure and specific volume and temperature data, all of that's related. And we have it in a graphical form, but we also have it in a tabular form. So we have thermodynamic tables that we can look properties up in. So let's we're not going to pull properties out of our tables yet, but let's sort of introduce that concept. And before we get there, we need to know, well, how many properties do I need to be able to know where to go in those tables? Okay, and so that's given by our state principles. So for a simple compressible system, two intensive independent properties are required to fix the state of our system. So, well, let's kind of go break it down, okay? So simple just means that we don't have anything crazy going on. It's simple, right? No electrical, magnetic, gravitational, motion, or surface tension effects. Compressible means that the specific volume can change, or, we might be more comfortable saying that the density can change. Intensive. Well, we know what that means. Intensive means that it is independent of the size or the mass of the system. So temperature, pressure, and specific volume all fall into that category. Okay, all right, perfect. Independent. Well, when we say independent, we mean that just because one of those properties changes doesn't mean that the other property will as well. Okay, so they are independent of one another. All right, so we have to check all those boxes to be able to fix our state. So let's look at all three of those. So temperature and specific volume, always independent, which means that if you know temperature and specific volume, you can fix your state. You could pull out, and remember, fix your state means that I can figure out anything else I want to know about that system, any other properties that I want to know about that system. So temperature and specific volume, check, always independent. Pressure and specific volume, check, always independent of one another, and they will check the box and be able to allow you to fix the state. Temperature and pressure, though, you have to be careful. If it's in a single phase, meaning you have all liquid, all vapor, right, or all solid, it's only, they're independent of one another in a single phase. But if you are in that region of saturation, it does not work, okay? So let's kind of look at this guy right here. So temperature and pressure. So if we're in a single phase, if I know that I'm at T1 and P1, okay, well, it could be a saturated liquid. It could be a saturated vapor, but it could also be somewhere in the middle. So I don't have enough information to fix my state completely. Let's look at the temperature and specific volume and pressure and specific volume. So let's look at the top one. So if I knew that I was at this temperature and let's say this specific volume, well, I'd go look at that, basically that coordinate. Oh, I'm two-phase, right? If I knew the pressure and the specific volume, let's say I'm at P2. Let's say I know that whatever this P2 is, I don't know what that is. Let's say it's 50 bar. Let's say it's 50 bar, okay? So I know I'm at this P2 50 bar, and I know what my specific volume is. Well, if it's right here, I know it's two-phase. But let's say it's over here. I know my specific volume is right here, and if I could read it, if I had numbers down here, I could see, well, it'd run into that P2 right there. I would know that I was superheated. So temperature and specific volume, always independent. Pressure and specific volume, always independent, always enough to fix your state. But temperature and pressure, only if you're liquid, all liquid, or only if you're all vapor. Yeah, so in a single phase. All right, so that's all we got. And the next thing we're going to do is start looking up properties. All right, thanks for watching. Let me know if you have any questions.